Hi, my name is John Helfin. I am an education solutions specialist with Autodesk, and today I wanted to provide an overview of the finite element analysis environment, or the FEA environment, and also the dynamic simulation environment in Inventor. And really I want to look at how those two environments work together. You can actually use the dynamic simulation environment to generate real-world loads that can be applied to a part in a stress analysis. So for this presentation, I actually decided to create a trebuchet, which is essentially a catapult of sorts. Historically, it's been made of wood, but I figured why not modernize it for Inventor, and I went ahead and created the parts in Inventor as milled aluminum components, and I've assembled them so that in the assembly environment, if I click and drag, you can actually see that they move as you might expect, rotating around the shaft in the center. So to start out, what I wanted to do was first do an FEA analysis on this arm here in the center, and then I'm going to go through and set up a simulation where we'll actually do a simulation of launching the projectile using the trebuchet, and then we'll collect the forces that are generated during that simulation and rerun that analysis on that same part at the end. So to get started, I'm going to go ahead and right click and open this component in its own window so we can focus on it, and I will jump into the stress analysis environment. You can get to it from the environments tab on the ribbon bar and the stress analysis icon. So when you jump into the stress analysis environment, it actually changes just in a similar fashion to moving into sketch or assembly mode. It automatically adjusts all the tools that you would need to do an FEA simulation. So to get started, we can create a simulation using the icon on the left, and that brings up this new simulation dialog. Now we're going to go ahead and create a static analysis, single point analysis. Inventor also has the ability to do a parametric dimension analysis, where you could change or set a range of sizes for specific features in the model to run multiple simulations at once to find out which one is the least amount of weight with the highest safety factor, for example. But in this case, we're going to start out with just a basic single point analysis. So I'm going to go ahead and hit OK, and the browser actually pre-populates or creates, essentially areas in the browser where we're going to collect information as we set up this simulation. So the browser from top to bottom works the same as the ribbon bar from left to right, and it's generally in the same. You don't have to follow this workflow, but it generally is a nice workflow working from left to right to get to the simulation. We're not doing a parametric table, so we're going to go ahead and skip that. But you do have the ability to assign materials. It will bring over the material from the assembly or the part if you've already assigned it. If you wanted to, say we didn't want to use aluminum, we wanted to override just for the simulation, we wanted to override it with cast iron or steel, we could do that here. But we're going to go ahead and leave the defaults for now. Next are constraints. And we're just going to use a single fixed constraint to start out. We're going to fix this center point, which is where the shaft would rotate around the arm would rotate around the shaft. I'm going to go ahead and apply that. When you do that, you can actually see the browser has been populated with a new fixed constraint. So if we wanted to, we could come back and highlight this or hover over it and get it feedback as to where it is in the model. In this situation, this is not hugely important, but as things get more complex, it's useful to be able to come find something in the browser and see it where it is on the actual model itself. So next we're going to go ahead and create some forces to apply to the model. In this case, we're going to use the hole on each end as the place to apply the force. And here, when I selected it, it puts the force in at a strange angle. If I had straight lines in this assembly, or in this part, I could actually just select a straight line to align the vector, the force vector. In this case, I'm going to go ahead and use vector components, and this is just a way to manually place forces in a specific direction. So we're going to put it in this Z direction here. And I'm going to go ahead and apply that, and you can see that the force has been aligned to the Z in this part. I'm going to go ahead and do the same thing at the other end. It keeps the same settings from the last one, 150 pounds in the Z direction. I'm going to apply that. And now we actually have everything we need to actually run the analysis. But before we do that, I wanted to show one more. It's in the one more item. It's in the prepare section, and that's mesh view. I'm going to go ahead and click that and let it calculate the mesh. So what it's doing is actually generating the mesh that will be used to calculate all the stresses. And once that's, oh, here we go. Now you can actually see the mesh that's going to be used to run the FEA analysis. Now, the reason I bring it up is a couple of reasons. First, if you run the mesh first, you can make sure that everything looks all right, and it speeds up the actual simulation time because it doesn't have to calculate the mesh at the same time. But really, if you zoom in on this fillet corner, you can see it's a little bit choppy. You can set in the stress analysis settings on the toolbar, you can actually set the size of the elements, and that is meaning the triangles that are used to generate the mesh. You can change that for the overall model, or you can actually use what's called local mesh control, which will give you the ability to tighten up the mesh in just a small region. And that's useful in that you don't actually have to shrink the number of elements across all these flat faces, because that really isn't useful. But in the corners, the smaller the mesh, the more numbers of points of calculation will take place. So you'll actually get a much more accurate reading. And in the corners or tight spots, that's, can be useful. So let me go ahead and put in a smaller number here and pick this corner face. And I'll go ahead and hit OK. And you can see as soon as I hit OK, it tells me that my mesh is out of date here in the browser with the red lightning bolt. I'm going to right click and hit Update Mesh. And it's going to recalculate that, but it's going to take into account the change we made just for that face. And when it completes, you'll actually see this is going to look much smoother. Instead of these long triangles, you get more, a larger number of triangles, and essentially it is generating a larger number of points of calculation, so you'll get a more accurate result. Now keep in mind, the smaller the elements, the more number of points are going to be calculated, and the more powerful or more time your computer will need to be, or the longer it will actually take to run those calculations. So you'll want to keep that in mind when you're adjusting these settings. But I'm going to go ahead and zoom back out, and I'm going to actually turn off the mesh now, and we'll go ahead and run the simulation. And since we already built the mesh, here it's just going to compute results. If we hadn't done the mesh yet, it would actually compute the mesh now. And what we end up with is the stress analysis results. Now, by default, the system actually scales the results. Here I'm going to go and put, normally the default looks like this, where the results are adjusted or essentially scaled so that you can actually see a very large change, so you can actually visualize or better visualize where the changes and problems would occur. If you increase to a 5, you can actually see it jumps out really pretty obnoxiously. But if you jump back to actual, you can actually see what the actual deformation and stresses are. Comes in handy if it's only a minor change to actually get the scaling, so you can see where things are taking place. Some nice things to call out. Here we're looking at the von Mises stress. On the toolbar we actually have, and right now because I'm in only a 1024 by 768, I don't see the labels, but in a larger resolution you actually get labels for all of these buttons. But there's actually toggles here where we can see, if we want to quickly see where the maximum stress is, we can click that toggle, and it actually puts a pointer right to where the maximum stress is here. Okay. There's also one for minimum, which is actually, let me zoom back out. There's the minimum here. But if you wanted to pick your own locations, you could do that as well with a probe. That's what these are actually probes. So if within this green area here, we could go ahead and place a probe, and it will actually show you the results. Along with that, we can actually go to animate this and actually see how the stresses are applied throughout the range of the analysis. So you can actually see how much it's deforming here, and you can see where the stresses are being applied, and you can also see all these probes updating dynamically. So you can actually read how those stresses are being applied throughout the animation. So last but not least, let's look over here in the browser. We've got in the results area, we've got the von Mises stress, we've got first and third principle stresses. We also have displacement. You can obviously see here's the largest displacement is right here at the end, and also safety factor. Now, in this case, I wanted to look at this because here I can see the safety factor is actually below 1, which is bad. It means that the material will not handle the stresses that we've applied, or the forces that we've applied to the part. So one of the nice things about the way the simulation environment is set up in Inventor is I can actually look at some results and make decisions and adjustments on the fly. So now here in the browser you can see simulation 1. I'm going to actually right click on that and I can copy this simulation. So you can actually have multiple simulations in the same environment, and we can choose to or when we copy that, it essentially brings through everything. It's an exact duplicate. The same constraints, same loads. But what's important for that is we've run that simulation on simulation 1. And here in simulation 2, we're going to actually expand the part model in the browser. And one of the ways that we could look to get that safety factor above a 1 is potentially removing this pocket, which will make the part heavier. These pockets were really just added to reduce weight, but we could remove that, which should make it stronger, but it also makes it weigh more. So what we can do is in the browser, go ahead and exclude that extrusion from the simulation. And just like suppressing a part or suppressing a feature in the part model, it also suppresses its dependent features as well. So with that suppressed, we can go ahead and rerun the simulation. And here you're going to actually see it's computing the mesh because it changed the model. So it's regenerating the mesh. And then it's going to also run and generate the results too. Okay, so now it's done that. And here we can jump down to our safety factor in the second simulation. And you can see that now our minimum safety factor is 1.06. So really by removing that, suppressing that, or removing that component or that pocket, we've actually increased the safety factor to above 1, which means now essentially the part will just barely handle the stresses and forces that we've applied to the part. So you can see in Inventor, it's a nice, easy, simple way to run a test, evaluate the results, and then make changes and reevaluate those very quickly in the stress analysis environment. So I'm going to go ahead and finish up this basic FEA component of the demo, and we'll switch back over to begin setting up the dynamic simulation, and then we'll rerun a more advanced stress analysis after that. Thanks. Hi, my name is John Helfin, and I am an Education Solution Specialist with Autodesk. And today I wanted to provide an overview of the dynamic simulation environment. This is actually step 2 in a 3-part series. The first step was a basic FEA component. In this session, we'll walk through setting up a dynamic simulation that exports motion loads to FEA, and then we'll follow up with a third demonstration that shows how to load those motion loads into the FEA system to complete your analysis. So, as an overview, this project is a trebuchet that historically is a wooden structure, but I've chosen to modernize it in Inventor for this demonstration. So, to get started, I'm going to enter the dynamic simulation environment. And you can find that on the Environments tab. On the far left, there's a dynamic simulation option. And that actually will change, turn on the dynamic simulation tab here and convert the user interface to show the tools that are used in this environment. Very similar to the way Sketch and Assembly work as well. Inventor automatically sets the tooling or the tools up to accomplish the task at hand. So as we get started, let's first talk about what happens when we come into the environment. So first you notice that the browser has changed. What has happened is by default the simulation environment actually looks at all the work you've done in the assembly world, and it will take all the constraints and convert those automatically to simulation joints. It also organizes your model components into specific groups. For example, the grounded group is a list of all the feature or parts that have been physically grounded or are constrained in a manner that will cause them to be grounded. You will also see things that have no constraints placed in the grounded group. The next thing that you'll see is the mobile groups, and those are things that are moving in the assembly, things that are mobile. Next, you've got standard joints. Those standard joints are all the assembly constraints that have been, or that were applied in the assembly model and that have been converted to standard joints in the simulation, are placed in the standard joints section. Next, you have force joints. Force joints are the constraints we're actually going to add. 3D contact joints, any joint that has components interacting with each other. And last but not least is the external loads, and that is loads, for example, like gravity, or if you have an assembly component that isn't complete and you want to represent the force that it's going to have on this dynamic simulation, you can actually represent that here in external loads as well. So again, these are all automatically created for you. The very first time you come in, you will not see force joints because you will have not created any yet. But what I'm going to do to make sure nobody thinks there's any magic happening or any man behind the curtain, I'm actually going to show you how to turn that automatic conversion off. We're going to essentially reset the system. So if you go to simulation settings, there's an option that says automatically convert these constraints. So if you chose not to have the system automatically convert things for you, you could uncheck this checkbox and it's going to tell you that it's going to delete everything. And I actually am, in this case, going to use it to reset everything so that we can walk through the setup of this. But you could do this and leave it set this way if you don't want the system to automatically generate constraints for you or joints for you. So when I apply that, it's going to actually clear out the browser, and you can see that it's removed the majority of things and put everything in the grounded group or left the grounded and external loads groups. So I'm actually going to check this checkbox again and hit apply, and it will actually regenerate all of the automatic constraints or automatic joints that we had in the first place. The one thing that's missing is those force joints. So we'll go ahead and recreate this simulation from scratch, and I'll walk through exporting to FEA. So before I actually get started with any simulation or creation of joints or anything like that, I actually want to confirm that the actual automatic constraints were created properly. I don't generally trust software until I know it's been proven and I've seen it actually do what I expected it to do. So here in the results section, there is a dynamic motion option. And what this does is when I click that, it's going to convert the simulation player to a dynamic motion player. which essentially lets you, similar to the way assemblies work, click and drag to create motion. In this case, it's actually clicking and dragging and applying a force. But if I click and drag and let go, it applies that force to the weight, and you can actually see the model moving. And in this case, it's actually doing what I would have expected. It's respecting the constraints that were applied during the assembly mode, but it's, the parts are bleeding into each other, so there's still work that has to be done, but the motion itself is correct. So I'm going to go ahead and hit the delete or exit button here, and that actually will return me to the normal simulation mode and reset all the parts back to where they were. So now that we know everything works the way it's supposed to, I'm going to go ahead and turn this to the side, and I'm going to actually start the simulation just to see where we're at. So I'm going to hit play. What you can see is the simulation player is actually running. It is doing something, but in this case, nothing's happening in the model, and that is because we have not applied any forces to the system yet. So right off the bat, a trebuchet is a gravity-driven mechanism. So I'm going to actually go into construction mode here on the simulation player. There's a toggle, a construction mode toggle that lets you jump into construction mode, and where you can actually create joints and forces and set the simulation up. So back in the browser under external loads, we had gravity, and I'm going to actually turn that back on so that we can have our first force or first item in the simulation. So right now it's suppressed. If we unsuppress this, you can actually see the vector of where the gravity is currently set up. I'm actually going to go ahead and pick this bottom corner of the ground plane, and you can see that it aligns with that. If I wanted to reverse that or change that, I could actually, just like in an extrude, flip the direction with the toggle here in the dialog. Or if I wanted to, I could use vector components and actually manually define the direction of the gravity. In this case, we'll go ahead and leave it lined up the way it is. And we can actually rerun this simulation. So now, if I start the simulation, you can see there is actual motion taking place in the assembly. What clicking play does is essentially release that weight that was positioned up in a higher spot and let the force of gravity on that weight be applied to the system. So here you can actually see it working the way I would have expected. Again, the motion is the same as we saw when we were testing it in the dynamic system or dynamic mode. And now we can see that with gravity everything is working. What we want to look at now is what's going wrong. What do we need to work on? If you go ahead and hit play, well, I'll stop this. Actually, once you've played this, you can actually use the slider to walk through the steps of the simulation. And right out of the gate, I can see one problem, and that is that the arm falls through the floor. And that's not supposed to happen. We want it to drag along the floor before it lifts off. So we can begin adding constraints or joints to the system to actually solve that problem. But before we do, I wanted to go into another component that we can use to kind of help us with this setup, and that's the output grapher. An output grapher is essentially a graph of data about the model, and information such as the forces or positions of specific joints in the model, accelerations, velocities, but more what I was specifically coming in here to do, and we'll go through the output grapher throughout the demonstration, but what I wanted to do is actually look at tracers, or add traces. So a trace is actually a point within the model that is important to you. So I'm actually going to right click on add, or on the trace option here, and select add trace. And what you'll see is you get a dialog box where you can add the tracer. The first column is the display, so what's going to be displayed in the scene itself. And right now, trajectory is selected. The next column is output value or output information, so what information is going to be collected. And I'm going to go ahead and check all those. I'm actually going to set my trace to pink because it stands out on the gray background. And I'm actually going to zoom in into the model and pick a specific point. And that point is right here at the end of the arm. So if I apply that and cancel out of this dialog box, now in the output grapher you can see that I have a new trace, and I'm going to actually rename this while I'm here because we're going to add more later in the demonstration and I don't want to get them confused. So I'll name that one arm. And here you can actually see I've got position graphs for the simulation. So I'm going to go ahead and turn on the Z dimension, which is the vertical dimension in the model. And the reason I wanted to do that is point out this graph. I'm using the middle mouse button to actually zoom and pan in the graph, but I wanted to zoom in on this starting point. This starting point actually, 0 is where the ground plane is located. So if you look at this trace, what I'm seeing here is that just before or just after we start the simulation, the arm drops into a negative position. So if we play let me get the simulation player out from behind that dialog box. And let's go ahead and play this, and you can see the graph and the simulation running at the same time. So right when we start, you'll see the arm drop along with the graph. So this is providing you information in a graphical and visual format in the scene as to what's happening in the simulation. I wanted to call out this specific point because we're going to actually, with the first joint, fix this. And it will change the graph and the tracer. So I'm going to go ahead and close the graph for now. Let's jump back to construction mode, and we can go ahead and make our first joint to work on making the arm drag along the floor. So in construction mode, the insert joint option becomes available. And when I click on that, I'm going to get my insert joint dialog. And in this dialog, you get a drop down with a list of all the different constraints or joints you can actually create with an animated preview as to what that's actually going to do or create in the model. So here you can see a gear, and a spur gear and a running along in the animation. You could also see, for example, a cam and a follower. But you get an idea visually of what is going to be accomplished by each joint. In this case, we actually want to create a 3D contact joint, and that is going to tell these two components that they interact with each other. So I'm going to go ahead and zoom in on this arm, and we can start adding joints. So in this case, I want the ground plane, or the ground part, to interact with this arm. Now, I picked this face just because it's close to this and it's a quirk of mine. You can actually pick anywhere on the part, but I'm going to go ahead and apply that and cancel out of this dialog box. And now you actually see the force joints have been added back into the browser, and our first constraint is there, or first joint is there. So let me zoom to the side now. And let's rerun that. Let's turn the output grapher back on so we can actually see it running next to it. Here we go. So now when I hit play, what we'll see is the tracer start in the scene. And as you can see, instead of dropping through the floor, it's actually being dragged straight. And in the grapher, you can actually see the same result. Rather than dropping negative, it gets dragged along the floor before it takes off. So we've actually fixed the problem, the first problem that we had, and we can move on to looking at other components that need work. So let's go ahead and I'll stop this simulation and jump back. I'll center this. So the next item, if I drag through the simulation, so the next item that I notice is the ball. It's not being picked up by the arm. So we haven't told the system, the ball was not constrained to the arm in any way in the assembly mode. So we actually need to tell the system about the interactions of some of the components. And just like we did with the arm and the ground, we're going to add 3D contact joints. And I'm going to go ahead and jump into construction mode. And I'm going to actually add a few here since you've already seen me add one. They're all done in the same manner. I'm going to go ahead and insert a 3D contact. And the contact points are between the ball and the ground. We know those two need to touch. So I'm going to apply that. I also want the ball to interact with this arm. I'm going to apply that. And last but not least, I'm actually going to have the arm interact with this rubber stopper here. So now if I cancel out of that, you can see, we've got a bunch of new joints in the browser. And I'm going to turn to the front view. And go ahead and play that simulation now. Now, what you can see is the simulation is actually playing, and you can see the beginning of the tracer there. But what's happening is it's getting hung up on the ball. If you zoom in here, you can actually see that it is wobbling. Let me go ahead and stop it, and I'll start it one more time so you can see it up close. Let me rotate a little bit. There you go. So if we hit play now, you can see that it's getting hung up on the ball. And there's a reason for that. It's actually working the way it's supposed to. If we go into construction mode and we look at the grounded components, you can actually see that the projectile is listed as a grounded component. So what's happening is it's doing what it's supposed to. It's keeping the projectile grounded, and the arm is actually interacting with that, and it's getting hung up on it. And the reason it's grounded is I mentioned in the beginning of the demonstration that anything that doesn't have assembly constraints in the assembly mode is going to be placed in the grounded group. And this can be fixed with a spatial joint. So I'm going to go ahead and go back into the insert joint dialog box and look for a spatial joint. And what a spatial joint is a joint that tells the system that an item has full degrees of freedom. So in this case, I'm going to select the projectile, and normally, or in some cases, you'll need to use align the axes to other components in the assembly so that the model knows how to move within the system. But in this case, since it's a ball, we actually don't need to do that. I'm going to go ahead and click the second component being the arm, and I'm going to apply that. So by applying that spatial constraint, you can see, or spatial joint, the grounded components no longer has the projectile listed, and it's been moved to the mobile group. So before I rerun that, I want to jump back into our output grapher, and I'm going to actually add one more trace. I am going to add a trace to the projectile itself so we can actually watch what it's doing compared to what the arm's doing. I'm going to go ahead and make it a green trace, and I'm going to select the projectile. Apply that, cancel. Now, before we run the simulation, I'm going to go ahead and turn on its Z graph, just like we had in the arm. And I'm going to zoom back out, close this so we can actually run the simulation and see what happens. So now when we hit play, we can actually see multiple tracers running. We can see the pink one with the arm and the green one with the projectile. And now that we've added the spatial joint, you can actually see that the two are interacting properly. And here you can actually see the projectile being launched from the system. So let me open up the output grapher again while that's running in the background. And you can actually see in the graph the two positions, one from the arm tracer and one from the projectile tracer. And you can actually see the exact point at which they separate from each other. So let me go ahead and start that over again with the grapher running. And I'm going to move this out here so we can actually see it at the same time. But if we hit play again, Again, you can see both tracers running along the floor, or the zero plane. And as the ball picks up, you can actually see that at this point in the graph, you're going to see the ball separate. So you're actually getting information from the graph and visually from the scene itself. I'll go ahead and stop this. One of the other items in the output grapher that's nice is you actually have, along with the graph, you have the data that's generating the graph listed above it. And one of the things you can actually do that comes in very handy is right-click on one of those columns. In this case, I'm going to go to the projectile, and I'm going to right-click, and I'm going to say search for max. And it's actually going to jump the model to that position where we're at our peak of the trajectory. So this can also be done for finding, let's see, we can do find max, find mins, find the zero. So this comes in handy also when you're looking at forces. So you can quickly find the max force or the minimum force and the position and time at which that happens. We could, if we wanted to, check this checkbox under the FEA column and choose to export that to the FEA system. Now, in this case, we're going to actually do it slightly different. We're going to export a series of things to the FEA system. So I'm going to go ahead and close out of this graph run. I'm going to go into construction mode because in order to export something into construction or into the FEA system, you actually have to tell the simulation environment that you want to export it before you run a simulation so that it can collect the data needed to do the export. So on the toolbar, there's an export to FEA option. I'm going to select that, and I am going to export this arm. And when I hit OK, it's going to bring up a dialog. Because we're doing just a single part analysis here of this one part, it wants to know what the important surfaces are that are contacting other items in the simulation. So if I select this first one, it wants to know where the shaft surface is. I'm going to go to the next one, and it's going to actually just work its way through each of these components. And as you solve each of those issues, it will actually remove the exclamation point so you know that you're working through the list properly. So here we're going to actually select that interface there, and last but not least, we will do the screw hole where the rubber stopper is mounted. So if I hit OK there, I can zoom back out, and we're ready to do FEA. So in the output grapher, we'll bring that back up and do an update here. In the output grapher, if we expand that, the bottom option was export to FEA. And if I expand that now, we have the treb arm listed. So that's the one piece that we selected. The next item here is the time steps. So what that does, I'm going to actually run that simulation once so it can collect all the data while I'm talking about this. So the time steps are a way to set a specific number of steps throughout the simulation that you want to export, a specific number of time intervals. So we're going to let this go ahead and run, but once we're finished, again, we could go back and pick specific times from the graph, but I'm actually going to go ahead and just select like 25 different spots broken up evenly throughout the entire simulation to export to FEA. That way I can actually run different stress analysis simulations on different times in the assembly as I need to. All right, so it finished its simulation. I'm going to go ahead and right-click on the steps and select to generate a series. And by default, it selects 25, and that's fine for this in this case. You could also pick to do 25 only in the last half second of simulation. Or you can actually surround a specific time if you wanted to. But in this case, 25 is fine for this demonstration. So when I export that series, you can actually see a list of 25 time frames that have been exported from 0 to 1 second. So with that complete, we are actually in a position where we are ready to leave the dynamic simulation environment and continue on to run an FEA analysis using the motion loads that were just generated in this simulation. So we will, or I will return with a third component of this workshop shortly, and I look forward to talking to you again soon. Thanks. Hi, my name is John Helfen. I am an education solution specialist with Autodesk, and today I am finishing up a three-part workshop or demonstration on FEA and dynamic simulation. The first demonstration was basic FEA. The second demonstration was dynamic simulation. And the third will be leveraging the real-world forces generated during the dynamic simulation to rerun the original FEA, leveraging those loads. So just a quick overview, the project I'm using to do this demonstration is a trebuchet. Historically, they're wooden. I've modernized it for Inventor and created it out of milled aluminum. So hopefully you've seen the previous two workshops or demonstrations. If not, go ahead and step back for a minute and review those, because here we've actually are starting from a point where we've actually run the dynamic simulation and have collected the loads and forces that are generated during the simulation. So to finish up the series, I will enter the FEA environment, or the stress analysis environment, and I will create a new simulation. Now, previously, we had created just a single point static simulation and went ahead and clicked OK and started with the defaults. Here, since we've run through the simulation already and we told the simulation to export the loads and forces to the FEA system, we can actually use the motion loads analysis option here in the static analysis section. And when we check that checkbox, you can actually see that the part we exported, the treb arm, which is the arm here in the center, is listed. If we had selected multiple parts, we could select it, they would be listed here as well. After we had indicated that we wanted to export that part to FEA, we went ahead and generated a 25-step series of positions throughout the dynamic simulation, and you can see those here. So we're going to go ahead and just pick somewhere in the middle and hit OK. And what that will do is actually go and move the model into position at that time during the simulation, and it will automatically apply all the loads that were being generated on that part at that point in the simulation. So previously we had actually done the simulation or a stress analysis where we fixed the center point and we just put a single z-axis force on each of the holes on the end of the arm. And here you can actually see much more realistic loads being applied. You can see it's not just a single force. There's rotational and torsional forces being applied. There are external loads being applied here as well. So when you look at this, you can actually just see that there's significantly more information that is gathered from the dynamic simulation than what you might realize needs to be applied if you were to just do the FEA by itself on the arm itself. So since it gathered all that information from the system itself, all we actually have to do is go ahead and run this simulation now. So like I said, if nothing else, if you're headed towards stress analysis, if you can build a dynamic simulation, you're going to end up with much more accurate results, in my opinion, than you probably would have had you just done the static simulation by yourself. So here you can actually see the results of our simulation, and then you can actually see the twisting that will take place in this simulate or in this environment with the forces that are applied to this model. Now, again, like in the previous FEA demonstration, here we actually have the results scaled so that you can actually see the change. Let me go ahead and jump it up to, if I bump it up to a 5, you can actually really see how things are getting twisted. Of course, that's not the actual. Let's jump back to the actual results, and you can see that the twisting and the stress applied is actually very minimal. Let's look at the displacement. Yeah, you can see there's some displacement on this end. Let's look at the maximum. We can toggle on our maximum. Yep. Here, you can see on the end is where you're getting the max load. And overall, I would say, let's check the safety factor really quick. Yeah, the safety factor is plenty in this environment using all of the components that are part of this assembly. We are well within our safety factor. I mean, this is, just an aluminum trebuchet actually launching just a little rubber ball. So, we're definitely within our safety factors. So, as you can see, the combination of the dynamic simulation environment and FEA can really be worked together to generate everything you need to go ahead and evaluate your model in a digital prototyping method. Before we've even cut any parts, we actually get a good feeling of where things can be improved or whether or not we're gonna everything will pass based on the forces and loads we've applied. So I hope this was useful for everyone and look forward to presenting to you at another time. Thanks.
Hey everybody, Rob Coe here. Talk a little bit about what's new in Inventor 2011. In this episode, we're going to talk about the new frame analysis tools inside of Inventor. Now, the frame analysis tools are now fully integrated in with the frame generator. Frame analysis is going to offer a complete end-to-end digital prototyping environment. We're going to sketch out your frame structure, create the detailed design with frame members from our existing extensive library, and then quickly simulate the response of the frames to gravity and other loads in an easy to use, easy to understand environment. Let's take a look at what we've done here so far. We brought it into the new frame analysis environment, and as you can see, we can go ahead and change the scales of the nodes and the loads so that it gives us a little better view into the analysis, and it doesn't necessarily clutter up the screen with a bunch of icons, if you will. So let's go ahead and set the gravity, important in analysis, especially frame analysis, of course. And let's first go through and add a fixed constraint. Now, take a look at this. Floating your cursor over the icon, you're getting a real nice animation as to how to place this fixed constraint. So as you can see, grab that beam, place it at the bottom, click on the node, and just right click and repeat. Now you can also use the space bar to repeat your command to just continually add these fixed constraints right there on those nodes. Alright, now that we've got our fixed constraint, let's move on to the rest of this. Let's go ahead and add a continuous load. Now as you saw, this thing's going to hold up a pretty big robot, and that robot's going to be moving around, so this frame needs to be fairly robust. So let's go ahead and add a continuous load. And notice that I have the ability to control the magnitude, the direction, as well as the force that this continuous load is going to be bearing on this frame. So let's go ahead and adjust the angle here, and then determine the magnitude. Now, bouncing back and forth between the nodes is basically what changes your inputs. Right? So as you can see, I've got the continuous load on that, and let's just go ahead and simulate the results. Now let's take a peek at these results. As you can see, we zoom in here. We've got our displacement, and we can change the display to actual one-to-one, deformed, and so on and so forth. And of course, we can animate the results. So go ahead and click play here, and as we can see, as that load is applied, we can go ahead and animate the displacement. Now let's take a look at what other tools that we have to analyze the results. So if we expand here, we've got normal stress. Let's take a look at that. And we can see that there's quite a bit of stress on that. So let's go in and change the display of this and add a diagram to our results. Determine what we want for normal stresses, for shear stresses. Select the specific beams that we want to further analyze so we can figure out, well, how are we going to address this problem? We've got a significant amount of deformation and normal stresses on this particular beam, as well as the other one, obviously. So how are we going to address this particular design challenge? I've received now all the information that I need from the simulation to go ahead and make the appropriate design change. So let's go ahead and finish and go back into the modeling environment. I'm going to go into my frame generation tools. Go ahead and turn on our skeletal model here. And let's go ahead and insert a frame from our library. We'll simply change our standard, determine which family we want to pull from, and then determine a size. Now, once the size is selected, we simply select on the line there to place this component into the assembly. It's not like we had to draw the profile, extrude it, and then position it relative to the rest of the components. The frame generation tool allows me to grab from a standard library and quickly and easily place the component into the frame and integrate it in with the rest of the design. So I've added my two members, and as you can see, it's taking the entire length of that line. Well, that's not necessarily what I need for this component, so what I need to do is I need to trim it up. And again, with the frame generation tools, I have tools that allow me to trim to frame or miter corners or perform a notch. Here, I simply need to trim to a certain face. So I'll select the two that I need to trim, select the surface that I want to trim it to, and choose OK. Alright. So now that I have my frame all trimmed up here and I've added an additional framing member to it, let's go back in our frame analysis tool. Now it's going to reanalyze, see if there's any changes to it. Again, automatically applying the changes to this simulation. and simply hit the simulate button again. Now I'm going to get my new results based upon the changes in the design. As you can see, this environment, this frame analysis is fully integrated into the frame generator. It was able to recognize all the changes, significant difference in my displacement, significant difference in my normal stress, and now I have a much more robust frame to support the loads of that robot while it's in action. So as you can see with Inventor 2011, we've got features enhancements to simulation and visualization, including the ability to record animations of displacement and stress results over time. You can produce video output of the displacement animation. After running the analysis, you can take advantage of the report generation tools to present your results and embed graphics and animation into your reports.
Okay, so what we're going to be doing in this example is taking a look at Inventor 2011, making use of the frame generator for structural member design or static frame member design. Now, the first thing we're going to do is make use, inside of Inventor 2011, of the hundreds of thousands of different components inside our library to make use of all these different profiles. We don't have to manually create these different frame structures. Rather, we can use an existing sketch and extrude all those different profiles along all the different sketch lines instantaneously. After the different structural member components are completed, we can perfect the frame design by cutting and coping, mitering the different joints and components within the interface, and truly digital prototype the components before we start cutting steel. Now, the other things that we can do is we can actually go in here and start extending or trimming off specific componentry within the design so that we can perfect the design and also analyze the design downstream. So what we have digitally is what we're going to have in real life. So we're going to go ahead and do this. We're going to go ahead and trim off some different frame members. I simply select the different frame members that I want to trim, and in this case I'm going to go ahead and tell it what I want to cut off or what I want to trim to. So I'm simply going to select a face. I also have the capability within Autodesk Inventor 2011 to be able to cope around curved components or curved frame members very easily, and so the interface makes this a streamlined environment, so I don't have to think about the different angles that I'm actually cutting off. Rather, I can let the software make those calculations for me. Now, once I'm completed trimming off my frame members and completing my design, I now have the capability to actually analyze the design in an integrated format. So I don't have to leave the interface. I can simply stay within Inventor 2011 and do a full beam analysis on this component. So what I'm going to start off doing is creating some fixed components or fixed points for this frame where it's sitting on the floor. And after I'm done creating these different fixed components, I'm going to start adding force loads to this geometry. So I'm going to go ahead and inform Inventor where these force loads are and what the force loads are going to be in real life. Now, after I define some of these different force loads, I also have capability to easily adjust force loads in complex positions. So in this example here, I actually want to define where I want to position this central force load on this frame. And I also want to be able to go in here and further define some additional direction of this load. Now, I'm going to go ahead and give it a value of 1,250. And I also want to go in here and define a more complex angle. Very easily, I can simply drag my arrows in any direction and apply this force load. So Inventor 2011 really makes this easy for an end user to do this, and faster than anything else in industry. Once I'm completed with that, I run my results. I can animate those results and do a variety of different things, including reports and different things this way. Inventor 2011 makes this easier than ever before.
Inventor's frame design environment provides the tools to create and analyze complex frame assemblies. Fully integrated with Frame Generator, Frame Analysis offers a complete end-to-end digital prototyping environment. The assembly is automatically converted into idealized nodes and beams. You can define mechanical properties of beams and easily apply real-world physical constraints, such as pinned and fixed connections, to hold the frame in place. Add physical loading on beam elements to replicate applied forces and torques. Once the criteria are entered, you can run the simulation and analyze the resulting behavior. Results, such as stress and deformation, may be animated and recorded for better visualization. If changes are required, you can quickly modify your design in Frame Generator. Back in the frame analysis environment, a single update will refresh results incorporating the changes you made to the frame. When your simulation is complete, it's easy to generate custom reports that include only the relevant loads, constraints, and results.
What we're going to look at now is the frame generator environment inside Autodesk Inventor Professional 2009. Created freehand here, just a skeleton part, 24 inches high, 72 inches long, 48 inches wide. This is going to be the skeleton model for the frame that I'm going to build. So I've only got the one component here in my assembly. So I'm going to switch from the assembly to the frame generator panel. And in this environment, I've got a different set of icons. So to bring things in, you just go to Insert. This is going to pull the part members from our standard content library. I have my association that I can pull from. In this case, I'm going to use the ANSI. The different families. I have flat bar, tube, flat bar steel, rectangular square tubing, angle steel, equal and unequal, W shapes, S shapes. See all the different types that are available inside the software. So we can just pick one here and say, okay, we'll go with the square tube. Now we have the sizes. These range for the available sizes that are available based off the family we pick from the association. So in this case, I'm going to go with a 3x3x1/4. Now I can apply any of the preset materials that are in the software, or we can add these custom and add those to the styles library, and they would be there available as well. So in this case, I'm going to use the aluminum 6061. Now if I want a specific color, I can add one of those, but if I want to just leave it the as material, I can do that as well. I do have an orientation window here on the right side of the insert dialog box. This is just where the placement is going to be based off of the pick points or the line that we select. So in the placement options, I can get the edges of my skeleton part, or I can pick points. So for the part that I've got, I'm going to use the edges. And if I select this outer edge here and rotate the model around and zoom so we can see it, kind of see there, it's right center line based off this orientation. So we can adjust that if we want it to be the top and the outside of where we're putting this is where our gate needs to be. But I'm going to use the middle, the center line selection there. I can continue picking legs, or I can just drag a window around all of them. Drag a window around, I see it gets all of my sides for me here. I hit going to frame name of the assembly because we are in a different environment inside the assembly. And hit OK. Here are the 12 parts that it's adding for me. It's going to put these in my location where the active project file is. So I hit OK. And it'll take it a few seconds, but it builds through the parts here, and it's storing each one of these parts individually so that we can apply independent end treatments. So we see that we've got a lot of interference here. Well, I'm going to right click on my skeleton part and just turn off visibility and get it out of the way there. And now I've got options. I can miter, I can trim, notch, and so forth. So I'm going to use the miter here. And as we see a preview here, it's kind of showing by default it's set with a 0 offset. So if I pick one member, the arrow toggles to the next. I can pick the next member and hit apply. And we can see that we get a 40 miter right there in the corner. So I can continue picking these and get all the corners here, get the tops and bottoms. And just picking those. And get the last two right here. Okay, so getting those, now we can see that we have the vertical members running in top and bottom here. So we'll close the miter box. Well, these here we want to trim or extend these to a face. So the members we're going, we can select these multiples in a time. So I'll pick my 4 members, and now the face that I want to trim these to, I'm just going to select the top of this bottom tube that's here. Hit apply, and it's going to shorten these members. And I'm going to select these again. Right click continue, or select the next arrow and select the underside face of the top tube we have there and apply that. Now we have cleaned those up with the miter in the corner. We have shortened our vertical members there as well. We can change these out now if we decide our vertical legs need to be something other than the 3x3. Go to change. It's going to build the library up, pull in all the components from the content library. And in this case here, I'm going to go with the square, or I could change to a rectangle if I wanted to. I'm going to stay with the square, but I'm just going to pick a smaller size. So I'll go with a 2x2x1/4, and I'll change and use the same material here. Now I'll just kind of pick the different pieces here that I've got. So I want to change this corner here, and we'll change this to the 2x2x1/4. We see a preview there. I can apply that. Now this is just telling me, okay, it's going to produce a new file. It's not going to delete the one we've already created. Okay, and then it comes in right there. Now it retains the end treatments from the previous piece. So swapping those in and out makes that a lot easier. So if we're using this with the Vault tool, we've copied design, and we want to swap out members, we can do that and retain the end treatments that we have applied previously. So as you can see, we just take a skeleton file, we get it the shape of the frame that we want to create, we bring it and place that skeleton file into an assembly, we save the assembly, go into the frame generator environment, start inserting our parts where they need to be. We can offset those, we can change the orientation if they're outside or inside or with an offset of set dimension, get those where we want, apply the end treatments, and we have our frame.
All right, what we're going to take a look at now is mating inside of Autodesk Inventor 2011. This is the easiest to use mating conditions on the market available. Nothing's going to be easier, nothing's going to be faster. Let's take a look. We have one tool that allows us to create a variety of types of constraints or mating conditions within the interface. Autodesk Inventor is easier to use than ever before. It's also the most competitive mating tool on the market to date. So we simply grab our tool. We can remake use of that tool by grabbing axis-to-axis mates, face-to-face mates, edge-to-edge mates, edge-to-face mates, a variety of different types of constraints that we can add within the interface. And it's easily as a click of a button. We select which axis we want to align to and which axis we want to align from. Everything's completed. Now, the tools also has some intelligence built into it. So in this example here, I want to go ahead and mate up some different types of geometry, one cylinder to another, and then I also want to go further in depth as far as what types of additional mating considerations I want to make on this component so that things move in relation to each other. Very easily I can bring up that mating condition relationship or that mating condition interface, and on the fly select the face that I want to mate from and select the cylindrical face I want to mate to, and continue to add additional reference mates to this component. So very easy to use inside of Autodesk Inventor 2011. And this is the only interface which makes mating conditions in a complex 3D environment so easy. It's going to make it possible for our customers coming from AutoCAD as well as competitive products to more easily move into the Inventor 2011 interface.
Hi, this is Frank Carmody. We're going to go ahead and explore more constraining today. So we're going to create an assembly file and then look at the tangential constraints. So I'm just going to go ahead and create an assembly. We're not going to create the component part files today. Those should be easy to create at this point, so we're just going to use a couple of example part files. Okay, so we're going to go ahead and put place component. I'm going to choose my example rectangular solid. Click open. This is 1 by 4 by 2 rectangular solid, so I click what places one automatically. Click again to place again. To place a second one. Click place again. And I'm going to go ahead and open up an example cylinder. Okay, right click and done to the cylinder. And now we're going to constrain the blocks so that
they're going to be, we can have kind of an angle between the two blocks, and then we can the cylinder then in that angle. So we're going to go ahead and flush up the side. So I click mate and flush, click two side flush. Okay, we're going to take our cube, kind of spin it back around, and now you're going to see that I can only open and close this block, or the set of blocks, like so. So they're all set to create our angle between. Now it's an interesting trick with Inventor. Let's take the order that I click on the constraints matters. So let's take our degree. If I click the bottom surface first, I'm going to do the two top facing surfaces of my rectangular solid. So I'm going to click the bottom one first, and then the second. And I'm going to set it to a 45-degree angle. And you'll see what happens in the example. If you can't see, let me go ahead and zoom in on that. You see what happens here. Now, obviously that isn't what I wanted to happen, so I'm going to click cancel. Now let's take the same constraint, but I'm going to apply it in the opposite order. So we're going to do a degree. So I'm going to click on the top of the top-facing second one, the very top surface. Then I'm going to click on the bottom, the top-facing surface of the bottom rectangle. And then I'm going to change that to 45 degrees. And this gives us our desired result. So you can see that in Inventor, sometimes it's not intuitive as to what will happen. And, you know, it's a good idea if something doesn't go right, that doesn't seem right to you, just assume that it's not a, Inventor isn't always intuitive. So go ahead and experiment a little bit with that. Okay, so now we're going to do the tangent constraints. So let's say that I want to fit this cylinder right in between these two blocks. So we're going to go ahead and select tangent. The outside tangent is already selected, so I'm going to go ahead and select my cylinder and the face of my block. Okay, now notice it goes into the block itself, so if I were to cancel out and drag this around a little bit, notice I can drag it. Now, it's very hard to see. It looks like the block is moving up and down, but in fact it's moving very far out in distance. So if I move this over here, or move the block just up, watch where that block actually went. If I go to zoom all. Okay, so this is actually way out in space here. Oops, not that far out in space. If you go to the wrong view, you can't really tell that it's tangent, but if you then roll the cube around, you can see that it actually stays tangent to the block. Notice I'm trying to move this up and down. Okay, so the next thing we're going to do is apply the next tangent constraint. So we're going to go to constraint. The trick I was trying to show you there is if all of a sudden you can't find a part, just click zoom all, and it's probably that you've moved it and didn't realize you were moving it way out into three-dimensional space. Okay, so we're going to go ahead and make another tangent constraint, clicking the cylinder first, and then the bottom face of the top block, and we'll click apply. Okay, so there we have the two tangential constraints, and basically what's happened is the cylinder is now constrained here between the two blocks. The last thing that we want to do to fully constrain that cylinder is to add one final constraint. It's a mate flush, and that's going to put the cylinder right up against the back of the block. And I go ahead and click apply. Okay, so there we have it. Good luck. Your assignment is to create a tangential constraint just as I have here. Thank you very much.
Think of assembly constraints as the 3D version of sketch constraints you've already used while designing parts. These are tools that help you create relationships in 3D between components, such as making two components flush with each other, making two cylindrical components concentric, or even tangent. There are lots of different ways to constrain assembly items, but they all essentially work to remove degrees of freedom from components as you add them. Eliminating degrees of freedom allows parts to be attached just like they would in real life. The most common way to add constraints is with the Constrain tool found in the Position panel. This brings up a window where you can define how parts will be constrained with each other. There are 4 tabs in the window. but we'll only be working with the Assembly tab for now, since it contains the most frequently used tools. The 4 types of assembly constraints are mate, angle, tangent, and insert. In this lesson, I'll be going over the mate constraint, which is a powerful and versatile constraint. When constraining parts, you can select points, edges, faces, axes, and planes. Each selection will have a different effect, and your selection will depend on your desired result. To get started, I'll constrain the hole in the wheel to the cylindrical hole in the bracket. When working with circular edges or cylinders, Inventor will allow me to select the cylindrical face, which highlights the axis of rotation, or I can select the circular edge. In this case, I want the 2 axes to line up, so I'll be sure to click on the cylindrical faces. As soon as I make the second selection, the component snaps into place, and I can click Apply to add the constraint. The Place Constraints window remains active, which is nice because it usually takes more than one constraint to assemble components, but I'll close it for just a moment. If I click and drag the wheel, notice I can only move it along the cylindrical axis of both the wheel and the hole in the bracket because of the constraint we added. I've locked down some of the degrees of freedom, but not all. This is the basic approach to assemblies. Bring in a part that is completely free to move in space, then add constraints to restrict this movement. I'll once again click Constrain to eliminate more of the degrees of freedom. Next, I need to center the wheel between the 2 flanges of the bracket. There are a few ways to do this. Here's one approach. If I click on one of the faces of the wheel, and then the flat face of the bracket, you can see this mates the 2 faces together. And if I look straight on with the assembly, this is clear. But we want to center it, so notice the offset box here. If I were to measure the distance, I would know how much to offset it from the flat face. I can type in a positive or negative value here. But what would this do for our design intent? If the bracket were to ever get wider, then using this approach would always keep the wheel offset with whatever value I type in here. So let's look at another approach. When we designed these parts, we incorporated some symmetry, which left the default reference planes of each part running straight through the center of each. We can take advantage of those reference planes when we add the constraints. To do this, I must expand each item in the browser. When I expand the Origin folder, I can hover my mouse over the planes to see a preview, and select it when I see the plane that runs through the center. If I didn't have these default planes here, I could always create new planes to mate. As you become more experienced, you'll find that you'll be thinking ahead as you design parts to have the reference planes end up in places where they help you at the assembly level like we have here. As soon as I select the other plane, it snaps into place. Notice they highlight in colors that correspond to the color of the selection buttons. If I again look straight on with the assembly, you can see it's centered within the bracket. Because of the design intent we incorporated with this approach, if any components get wider in the future, they would still remain centered here. At this point, all I have to do is insert the pin. To do this, I'll select the cylindrical faces, and the pin snaps into the hole. I'll press Apply. At this point, if I click and try to move the pin, it's free to move on the axis. So to finish constraining it, I'll press the Selection 1 button and click the end face of the pin. Next, I'll click on one of the flat faces of the bracket, and it snaps into place. If the alignment is not what you were expecting, you can use the solution buttons to flip the alignment. I can either mate the faces together or make them flush. The pictures are helpful in determining which alignment to use. In either case, you can still apply an offset with a positive or negative value. Once it looks good, just click Apply. and close the constraint window. Before concluding this lesson, I want to point out that all of the constraints we added are listed here in the browser. If I hover over them, you can see they highlight in the design window. As you might expect, these constraints can be edited or deleted just like features you've seen up to this point. Just right-click, select Edit, and the same window appears.